Hello, I'm Derek Hitchins. I'm on a mission to find out just what is systems engineering. We sent out our roving reporter to do some investigation. Hello, Derek. I've been out and about trying to find out what systems engineering is. I have to tell you, it's not at all clear from the people I have been talking to. Here are some of the ideas I came across. Something to do with computers. Anyway, that's what the woman in the street and the man on the Clapham omnibus seem to think. Engineering done properly. Actually, I thought engineering done properly was engineering. Shows how much I know. The engineering of systems, obviously. The way he said obviously indicated I was an idiot, which may be true, but it's still not obvious to this idiot. Meeting customers' requirements. Only that doesn't define anything except service, perhaps. Whatever industry consensus says it is. Now that's a really great idea. Not. Consensus just means that everyone can be wrong together. Shorthand for CGI systems engineering. That from film animation experts, computer generated imagery and all that. Invented on the job to sort out problems. So invented on the fly, as it were, making systems engineering impossible to define, teach, or even apply. Oh, that's easy. Systems engineering is defined in MIL Standard 499AB, IEEE 1220, ISO 15288, etc. Everyone knows that. Only they don't, and it isn't defined, that is. MIL Standard 499 defines engineering management, that's its correct title, while IEEE 1220 guides enterprises or projects to a well-engineered solution for project-oriented systems. Oh, so that's engineering technological products then. And ISO 15288, supposedly about system lifecycle management, appears in reality to be technology lifecycle management. So none of these defines systems engineering. Unless, that is, some people think engineering management and systems engineering are the same thing. Finally, I was advised by some experts that systems engineering was indefinable, all things to all people, which, once again, would make it impossible to learn, apply, teach, or whatever. So systems engineering, which is often quoted as the power behind NASA's iconic Apollo missions to the moon and back, seems to lack any sensible modern definition. Back to you in the studio, Derek. Well, thank you for that, Derek. I think you better go out and do some more investigation. Hello, Derek. This is your roving reporter again. I'm on my holidays, of course. And let me see now. Oh yes, systems engineering is hard or soft, whatever that means. Creating technological artifacts. Addressing messy problems. I think that's what soft is. Creating socio-technical systems. Finding the optimal or the optimum solution to some problem. Getting the best operational performance from a set of parts. Interesting, nothing to do with manufacturing, nothing to do with technology, timeline management. Only for large, complex systems. And for any problem in any domain. Some differences there. Meanwhile, back to you in the studio. Well, I'm not sure how far we're getting with this. But yes, I think we're all pretty confused. Thank you, Derek. Let's try Aristotle. The whole is more than the sum of its part. The part is more than a fraction of the whole. Excuse me. So what is a system? Well, some people say it's an abstraction. There's nothing there really. It's a concept. It's illusory. It's never real. On the other hand, it's technology that does something. It's whatever I want to call a system. Somebody really said that. A whole comprising interacting parts. Sounds reasonable. A whole something complete. And that goes along with the original idea that a system was simply a whole something. Open or closed? Now what do they mean? Even more confused? Yes, I think I am. System open or closed? Well, closed means it has a boundary through which nothing can penetrate. Open? An open system exchanges energy, substance, and information with its environment. So is the solar system abstract, illusory, conceptual, open or closed, bounded, purposeful? Is a person a system, a team, a family? Is a human cell a system? Is a human cell open or closed? And if a system were truly closed, how would we even know it existed? Continuing the quest. A system is a dent in the fabric of entropy, order in the midst of disorder. Well, there's some truth in that. It's hard to argue with. It's a whole something complete. We've met that before. Comprising connected, interacting parts. Therefore internally dynamic. That's a bit new. Open with throughputs of substance, energy and information, so link processes from inflow to outflow of that substance, energy and information. Stabilizes dynamically, if at all, at high energy levels. Certainly true of all living systems. Part of some greater, wider whole containing other interacting systems. And you can see from the graphic systems within systems, and you can see exchange between systems, interactions between systems. But I think there's probably more to it than jelly. So a system is, well, man-made systems are organized and purposeful. Technology actually is not purposeful, although we may ascribe purpose to it. We call that purposive. People have purpose, and technology serves their purpose, or purposes. Together, people and technology are purposeful socio-technical systems. So man-made systems will generally be socio-technical. People are parts of the system, they're not adjuncts to it, they're not plug-ins. More likely, they are a focus of any system. Team, platoon, group, capability. They perform functions, undertake tasks, and they achieve purposes and goals, with or without technology. Wholes are, on the other hand, are complete processes. They're complete squadrons, planes, ships, tanks, men and machines as one. They're complete enterprises, industries, forces, economies, expeditions. So the key words here seem to be socio-technical and complete. So if that gives us a clue on systems, what is, or perhaps was, systems engineering? You can see a complex system doing its dynamic thing in the graphic. There is a continual history of tug of war between engineers and systems designers about what systems engineering is. Paradoxically, systems engineering was introduced because problems, designs, constructs became so complex in the 1950s and 60s that engineers and engineering managers could no longer cope. What was needed was a paradigm shift. One where you came to understand complex issues and problems and to synthesize solutions to those increasingly complex problems. To anticipate and prevent new solutions from creating new problems, so that new solutions would operate in harmony with their environment. The new paradigm formed around the theory and science of systems, which was developing rapidly in the 1950s. And here's the famous poached egg model, systems within systems. The system of interest there is the white circle, which sits with others inside a black circle, and inside the white circle are a red, blue and a green circles which represent subsystems. This paradigm shift became the new version of systems engineering. This was happening in the 50s and 60s. New ideas, principles, methods and practice from the emerging systems discipline took hold. System theory was introduced. Systems consist of open, interacting subsystems. There are a hierarchy of systems within systems. They encapsulate, conceal complexity. Systems perform functions, exhibit purposeful behavior. Subsystems interact to create emergent properties of the whole. So our simple poached egg diagram has to be seen as actually dynamic, constantly on the change, making design, and this is a quote from the time, like nailing jelly to a wall, but still doable. Systems engineering principles include synthesis, creating wholes, i.e. systems, by bringing parts together without any reduction. Synthesis enables non-linear solutions to be designed. Holism, addressing whole problems, creating whole solutions, where the whole is greater than the sum of its parts, and a part is considered only in context, never in isolation. Organicism, originally the organismic analogy. Systems behave like organisms: conception, birth, life cycle, death and replacement. The paradigm shift was underpinned by systems science, and that had lots of elements to it. The systems science of wholes to begin with, understanding systems as whole entity. Behavioural isomorphs, a recognition that lots of different physical systems could behave in exactly the same way. Science of complexity, understanding particularly of extended system behaviour. Flocks, shoals, colonies, so forth. By extension, that leads to understanding human group behaviour. And the science of chaos, which many engineers have deliberately put their head in the sand and don't wish to know about. There's deterministic chaos, self-organised criticality, etc. Then there's a systems approach. We've already seen that an open system exchanges energy, substance and information with and adapts to other systems within its environment. A human cell is an open system. So too are individuals, enterprises, transport system, teams, etc. That means they have a constant flow through. And in the abstract picture there you can see systems within systems within systems. And they're interacting and they're dynamic. To adopt the systems approach, well, how do you do that?
You situate the system of interest within the wider system, interacting with and adapting to other systems. That's the post-egg diagram again, if you think about it. Hence you understand, design, simulate, adjust the behaviour of the system of interest. Only in open, dynamic context, never in isolation. And this is obvious for biological systems. When if you want to adjust something going on within the human body, you don't cut a bit out and treat it in isolation, mend it as it were, and then put it back in and expect the whole thing to work. You have to do it while the system's in operation. It now became de rigueur for all systems and systems engineering. The systems engineering always took the systems approach from that point onwards. And it was adopted widely in social and life sciences besides systems engineering. The systems engineering paradigm sees world issues and problems as networks of systems within systems, functional and dysfunctional, interacting and adapting. It employs abstraction to avoid jumping to conclusions, what we call solution prejudice, and so to promote innovation. It's a hierarchy to manage complexity. System is an abstract entity with purposeful behaviour. So we can model and simulate interacting systems, observe the resultant overall behaviour in environment. Hence we get system design by synthesis or model-based systems engineering, where systems are people, teams, organisations, socio-technical systems, etc. Here's a diagram showing you broadly how the new systems engineering paradigm might operate as a methodology. And you start at the top left by identifying symptoms of the issue or problem that you're going to address. You use the systems to probe the problem space, seeking dysfunctional systems or interaction, and you develop a real-world model of dysfunctional systems and interactions. Not easy, but not that difficult either. From there you conceptualize the ideal world model, which would be free of all symptoms, and you use the real world model with all its dysfunctions to point you in the direction of the ideal solution. You then design the ideal solution, you optimize the design, you realize the design, and you create new open interacting adapting systems, or you may modify existing open interacting adapting systems and their interactions. Notice that at several stages throughout the exercise you're testing, and the test is always the same test. Does the design at this stage eliminate all of these symptoms of the issue or problem? If it does, yes. If it doesn't, do not proceed. You've done something wrong, or you haven't done enough. So there, in a nutshell, you can see the general idea of a methodology, or in this case it's a sort of problem-solving strategy within a methodology. Relevance of the new systems engineering paradigm. It works with what you might call non-corporeal functional entities in problem-solving and conceptual stages, and because of that it can be applied to just about any situation or problem or issue. Social, organisational, economic, ecological, industrial, governmental, global, climactic, energy, pollution, medical, military, and so on. The systems engineering paradigm is potentially so powerful that it promises to address any complex problem and provide a creative, innovative solution, provided there is one. Some issues and problems are insoluble. Well, with all this potential power, what went wrong? The paradigm shift, the new systems engineering paradigm, was an instant success actually, taken up by a major organisation addressing complex issues in uncharted waters. So atomic power, both in the US and the UK. NASA took it up, as we've seen already, with Gemini and Apollo. US Navy took it up with Aegis. The Western world took it up with the Strategic Defence Initiative. In the UK, particularly air defence and naval systems, and so on. Major stuff. System designers and systems engineers became a new elite. They spoke a new language, they had new practices, new principles, and from a distance others thought they were practicing some sort of arcane art. It was called that. Amongst the new elite there were not many traditional engineers. The new systems engineering essentially was nothing to do with. It was the antithesis even of classic engineering, and this created resentment and envy amongst traditional engineers. Only about 10 to 15% of engineers proved amenable to training in the new skills. Others were constrained by their rigid engineering training and backgrounds. So different parties with different agendas have over the years laid claim to the title systems engineering as describing what they do. This even at government level, even making for serious confusion and misunderstanding. What happened? Well, cash-strapped organisations decided to design their own system solutions. They thought it would be cheaper in the long run. System solutions comprise people, training, reorganisation, architecture, support, configuration, management, and may include technology products. So cash-strapped organisations specify requirements for industry to build the technology parts, the artifacts, the products to order. These are the technology parts only of any socio-technical systems. Many engineers prefer to work this way, and the customer gets what he wants. But will it solve his problem? Is it what he actually needs? Engineers, many of whom neither understood nor accepted the new SE paradigm, tried to reinvent systems engineering as being confined to developing, manufacturing, maintaining artifact technology. That, of course, is actually engineering management. US engineering management reputation was also tarnished by the phenomenal Japanese success, particularly in the automotive industries, which we saw in the 80s, 90s, and is currently still going. So, in the US, systems engineering was rebadged as systems engineering management, which was truncated to systems engineering. The systems was put in front of systems engineering management to make it sound sexier and more impressive. The result was an industry pastiche, a parody even, of the new systems engineering paradigm. But the new systems engineering paradigm lived on in academia and among previous systems engineering practitioners. So today, there are two systems engineering identities. A, we have what we might call systems technology engineering management. And that's what we've seen recently is about business, economics, reductionist practice, technological products and technology lifecycle management only. It's really engineering management. And B, they're still alive and well, the new systems engineering paradigm, or simply systems engineering. Problem-solving paradigm, it's a discipline, there's a methodology, there's theory, science, principles, tenets. It employs the systems approach and the scientific method, and it invokes innovation and it manages complexity. It has a broad applicability well beyond technology and including particularly socio-technical systems. The increasingly complex world about us needs both of these, but in particular it needs the real systems engineering. Hello, me again, back from my holidays and with a chance to think. So, have I fulfilled my mission? To find out what systems engineering really is? Curiously, I think I may have. And the clue comes from the observation that systems engineering includes working on already operational systems to improve or to optimize their performance. All of the different views of systems engineering, which we saw at the start, share one important aspect in common. They all consider as their system of interest a set of parts acting and interacting as a unified whole that performs with optimum effectiveness in some operational environment. This set of parts acting as a unified whole, performing with optimum effectiveness, applies in equal measure to, say, the objectives of a systems engineer, getting all the parts of some technological artifact to work together properly and effectively. Or to a systems architect, designing some future complex socio-technical air defence system. Or to the operational commander of that future air defence system, who is reducing delay times to scramble interceptors, streamlining procedures, minimizing intel delays, etc., all to improve responsiveness and hence overall defensive system performance. Moreover, this set of parts, acting as a unified whole, performing with optimum effectiveness, can apply equally to natural extended systems such as flocks of starlings, an army of soldier ants, or a hive of honeybees, or to any man-made system. For man-made systems at least, it suggests that what we might call the essence of systems engineering is in selecting the right parts, bringing them together in the right way, causing them to interact in the right way, and orchestrating such interactions to create requisite emergent properties. These emergent properties would include that the interacting parts form a unified or unitary whole, and that the operational performance was optimally effective, and in outcome that the problem which prompted the new or revised system in the first place was solved, resolved, or dissolved. And actually, when you think about it, these would be the emergent properties of natural extended systems too. So there we have it. Systems engineering is ultimately about synthesizing whole systems to perform with optimum effectiveness in their operational environment. Nature, it seems, has evolved its systems engineering capability presently beyond our comprehension. So we still have much to learn about systems and systems engineering. Phew. And goodbye until next time.